Okay, hello everybody. Whoa. So hello everybody. My name is Martin Carignan. As you can see, my primary language is French. Hopefully, with my accent, you'll still be able to understand the topic. That's why also it's written. That's why I have slides. So I'm from Canada, Quebec, and my background is. I have a bachelor in actuarial science, and I thought that was too hard to say in English. So that's why I did then a master's degree in statistics. And then I also did an MBA. Started as an industrial statistician, worked for 4 years for a pulp and paper company, then resigned, started my consulting firm, and I'm a consultant since 2000. Statistics, continuous improvement, Lean Six Sigma, doing a lot of that. And so my topic today, what I want to share with you is how we can use something called a soft sensor to reduce inspection, but also potentially improve the control we can have on a process, so reduce variation. While I'll do the presentation, I don't think, we're not such a, it's not a big group. So if you want, you can just unmute yourself. I don't know if you're allowed to do that. Are they?
Yeah, I think they can.
Okay, so you can just unmute yourself and ask me the question as we go. Of course, at the end, we'll have time for additional questions, but just raise your hand or just say, hey, Martin, I have a question. And then I'll answer them as we go.
You can also put stuff in the chat if you prefer, and we'll make sure it gets looked at too.
Okay, yeah, I'll rely on you for that because I'm still, I'm not really a chatting type of guy. So as a statistician, I love numbers. I hate people. So the context of this presentation is the fact that in many organizations, what we see is that we have a lot of process data. Those data are often captured automatically, stored in some systems, and they're from different sensors and transmitters. And often also we can use those data to predict some quality characteristics that we measure on the final product. And in this presentation, I'll show you how we can use those process measurements to predict the final inspection. And when we do that, we do what we build a soft sensor. So a prediction using process data of the final quality parameter. So in my presentation, I'll start by defining what is a soft sensor, the advantages of soft sensors. Then I'll show you the steps if you want to build a soft sensor. And then those steps, we'll go through all of them using an example, the example of a tensile strength lab test. And we'll end with a conclusion. So a soft sensor, in soft sensor, we have the term soft, and soft comes from software, because it's typically a value that comes from a model, an equation that we get from a software. So it's a calculated value. And the sensor part, because the model is predicting a value that would come from a hard measurement, what we call the hardware sensor. So as we can see here, we have so we use a set of different process variables, and then we build a model. And with that, we can predict a hard value that would be measured by a real life instrument. What are the advantages of having soft sensors? One of them is it allows to perform real-time monitoring and control, especially to do that when the factors that you use in the model are measured at a higher frequency than the quality characteristic of the hard measurement. So often we have sensors that are measuring almost continuously. So with them, if you have that, you can have actually a continuous measurement of the final quality rather than having those tests that you get, physical tests that you get every few hours. So that can be a big advantage if you want to better control your variation. Also, you can potentially estimate some parameters where sometimes it's hard to have the hardware sensor. So because it's you cannot buy the sensor, it's something you have to rent for some time, or it's not possible to keep a hardware sensor there installed continuously because of the environment. So sometimes it can actually help in understanding the quality there when it's not easy to measure with hardware. It can be a low-cost alternative because often those hardware devices, they need to be used by people. So it's more labor intensive. So when you have predictions, often it's a lower cost to get those values. So then also potentially reduce costs associated to lab resources, because you can potentially even reduce the lab testing because you have those soft sensors value. You can use the soft sensor also to create a redundant measure that will allow to check between prediction versus lab. And if we see a big gap, then ask what's the cause? Because sometimes the cause could be, okay, the soft sensor is decalibrated, but also the cause could be, for some reason, now it's the lab which is decalibrated. We potentially, perhaps because we have a new technician, or the hardware measurement system is badly calibrated. And the last one, but not the least, it can also help in understanding which factors are really affecting the response, the hard value, the quality you're measuring. And you can then use the soft sensor to increase your learning speed. And I'll show that at the end when you look at something called the residuals. Many of my clients, they did improve their learning by looking at that and then improving their model because they learned about other factors that were affecting quality over time. So if you want to build a soft sensor, so a model that predicts some quality characteristic, I suggest you go through 5 steps. So step 1 is identify what are some potential good predictors. So temperature, pressure, whatever, that could predict the quality characteristic you want, which is measured by the hardware. Then you collect the data on those, and typically you need to clean and screen the data because there could be junk in there. The third step, when you have a clean data set, is to select, train, validate the model. So it's actually building the soft sensor. When it's built and you assess that it's good enough, then the fourth step is start monitoring and potentially adjusting the process based on the predicted values. And the last step is very important also. It's similar to the control phase in a Six Sigma project, because we know that no model is good forever. So it is to monitor the model adequacy. So make sure that the prediction is not going out of whack over time. And if it does, identify why and then correct the situation. So on this slide, I know when I did my MBA, this is not a good slide because there's too many words. But also I learned a thing called the A3, which is if you can summarize it on a single page, it's because you understand it enough. So here you have on that page all the 5 steps defined in details. So I'll go into detail of each, and then we will apply those details to an example. So the step number 1, identifying the predictors. So there, what you want to do is, again, identifying some factors that have a good relationship with the quality characteristic you want to predict. And ideally, you should try to find factors that are measured more frequently than the quality characteristic, because then you will get really added value from the soft sensor, which is faster feedback on where the quality is going, because you will have very frequent predictions. Of course, the model will be able to predict the frequency of the prediction will be the frequency of the least frequent parameter in the model. When you've identified those, we collect the data, we go to step 2. So we need to make sure that the data first is reliable. So it does make sense. The numbers we get are making sense, and we actually continuously get those numbers. So perhaps because this could be an issue with the soft sensor, if for multiple reasons, the fact you stop getting values from those factors, then you will stop getting prediction. So making sure that you get consistent values and they make sense. To make sure they make sense, you need to make sure also that those factors, those sensors from which the data are coming are calibrated, that they're accurate enough. When you look at the data, assess if you see any outliers, try to understand why. Is there anything you could do to make sure that those won't be part of your future predictions? And potentially identify if you could put in place some basic rules that could automatically filter some obvious outliers. So again, to minimize the risk that you will get very bad predictions. So when you have a clean data set and some rules to improve the chances the data you get will make sense, the step number 3 is to select, train, and validate the model. So that's the fun statistical part where you get to build the prediction model based on the values you've collected from the different factors that you've identified in step 1. When you do build a model for prediction, it's not a bad idea to use a training set to build a model, and then to use a portion of the data that were not used to train the model as a validation set to confirm if the model can predict data that were not included in the data set that we used to build it. And of course, then evaluate if the model is adequate by comparing with inspected values and look at the residuals. When I say build the prediction model, of course, to build the model, there are multiple tools to do that. You can go from multiple linear regressions. You can use partial least square, neural networks, whatever your preferred modeling technique, depending on the type of factors which you think about including in your model. As an example, if those factors, they are correlated between each other, perhaps you will need to use something different from multiple linear regression. Perhaps something like partial least squares. So again, you adapt, you use the prediction technique, which is the best suited for the type of predictors and the situation you have. Step number 4, now that you have the model, you start monitoring. So you use your model, you predict the quality characteristic, and then you can start monitoring the quality using the prediction. Because it's a quality characteristic, you compare the value you get from the soft sensor to specs, then what I will suggest, I will show you an example in this presentation, is potentially to use tightened specs, just to make sure that you won't accept potentially a product which is bad just because of the prediction error. Because when you build a model for prediction, it comes with errors. So then if you want to manage the customer risk of getting a bad product, you could do that by tightening the specs. And the fifth step is making sure that the model stays adequate over time. To do that, I suggest you look at the residuals. Again, I'm going to show you an example of that. But a residual, it's the difference between the hardware value that we will call the true value and the predicted value. Of course, we would hope the difference between those two would be zero all the time. It won't be, but we expect those values to be around zero. And so we can monitor them just to make sure that they stay consistent over time and we don't get any trends with them or excessive outliers, excessive residuals. So a soft sensor can sound very sexy, but it doesn't apply to all situations. Because if you consider replacing a lab test with a soft sensor, typically I would recommend you do that on a process which shows a decent capability to meet the spec. Because as I said, when we build a model comes with error. And if often you are very close to the spec, you increase the chances of potentially making a bad decision on the product using the soft sensor if you are too close to the specs. As an example, so here we have in the upper right corner graph, we have an histogram, which is showing on the x-axis, the horizontal axis, it's the value we measured. So we have values between mostly 50 and 100. The two LSL and USL are the lower spec limit, upper spec limit. So we would hope that all the products would be within those two limits. The height of the bars that we're seeing there represents the frequency of the measurement found in the interval that we see. So we can see that we have a lot of values between 70 and 75 in that column because it's the highest column. But also because we have columns outside below the lower spec limit and above the upper spec limit, we know that we also have some products outside of spec. Actually, in this system, we have 2% of defects. In this situation, if you want to implement a soft sensor, we will add to those hard value measured there some model error that could potentially make us make a bad decision when we're around the spec, should we keep or reject the product because of the model error. So again, when you're in that situation, it can be a bit risky to implement a soft sensor to replace the hard measurement. However, in situation number 2, in this process, we see that the difference is actually we're lucky the specs are larger and we have a much better capability to meet those specs. And we have room for some measurement error there without potentially jeopardizing our capability to the risk of accepting a bad product. Why? Because we're far from producing bad products. So in this situation, it is a better place to implement, less risky to implement a soft sensor. So I know potentially up to now the concept is a little fuzzy. So I'll try to make it more practical with this example. And I took it's a real life example that I simplified a little especially the model part, so we can understand more easily the concepts here. So the context is the following. We have a hard measurement, which is a tensile strength. So it measured the strength of a paper strip. And it's an important quality characteristic of the product we make, which is paper. And we have specs for the tensile strength. The lower spec is 15, the upper spec is 85. Today, what we do, we perform a test on one product every hour. And just performing this test is taking 50% of the lab technician time. Also, because we destroy the product, it has some cost associated to that because we destroy the product when we do the test. Implementing a soft sensor in this situation could allow us to save some money by not having to destroy products to have a tensile strength value, and also free up time from the lab so that we can perform the test internally, because we have to outsource some of them today. So as I said earlier, one of the first thing I would check is this process, does it have some good capability to meet the spec? Because I know with the soft sensor, I'm gonna be adding error there. So I'm gonna be adding variation. So we did plot here the data on the tensile strength and the specs. So the two red lines are from 15 to 85, the two specs, and the blue bars are representing the values we obtained when we made the product. Potentially, it could be for the last year. And we see that we have a good capability at meeting the spec. So we have room for some additional variation there. We don't have that many products that are close to spec where it would be risky eventually to use the soft sensor to predict, are they really within or outside the spec?
Martin, do you have a rule of thumb? And I tell people that, you know, some people's thumbs are bigger than others, but do you have a rule of thumb for the CPK, how big it would need to be in order to feel comfortable with implementing a soft sensor?
The answer is, I would like to give you one, but you know, I could give you the standard one, 1.33, but that would be just because I would rely on what is commonly known. But actually, it depends a lot, because it also depends on what are the consequences. I just present the concept here, because if the consequences of sending to the client an out-of-spec product, it's not that bad, you know, then you can take more risk. I have some clients where when they have a capability index, if you know those, a capability index of 0.6, they're quite happy. Others, they want 2. Why? Because of the consequence of sending an out-of-spec product to the client. So unfortunately, it's hard for me to give one. I could give you one if I really knew your context, and then we could come up with one, but it really depends on consequences of sending bad products to clients.
Very good, thank you.
Now that we know that we have, let's say here, we would say we have a good enough candidate to build a soft sensor. So step number 1 that we see here is we need to identify predictors. The goal of this presentation is to present the concept. So to keep it simple here, I will assume that we identified 2 factors that could be good predictors of tensile strength. We have factor A, which we measured on every product by a transmitter, and factor B also, which is measured on every product by some type of inline automated testing equipment. And remember, we do a test here. It's every hour and 10 minutes. But today, what we do in the lab, so we take a sample every hour or so. Here, it's actually every 70 minutes. And we make a physical test, a physical tensile strength test. Whereas in between those samples, we do produce some products for which today we have no tensile value. However, if we are able to build a good soft sensor, because factor A and factor B, we have values for each of those products, we will be able to get a tensile value for each product, which we don't have today. So we did collect the values for factor A and factor B, and also the tensile strength that were associated to those values. So on the top graph here, you have the distribution of tensile strength for the values for the sample we collected. And underneath, you have for those products on which we measured tensile strength, what were the associated factor A and factor B values. And what we could see when we did the histogram, and here at the top, you see on top of the histogram, it's something called a box plot. We could see some outliers for factor A. And those were values that the value was 999. Of course, we knew that those values were not real values. They were actually happening when the sensor lost connection to the network. And then automatically the value that was entered in the database was 999. So what we did, just to make sure that we won't use those values eventually to do predictions, we did some formula program that would automatically replace the 999 values by missing values. So we won't use those values for to build a prediction. And what we saw for factor B were actually all those values made sense. There were no outliers. So that's of course, I made it very simple, but typically step 2 cleaning and screening can take some time, where you try to find all those things where you could eventually put rules to make sure that at the end you get cleaner data. So now that we know we have a clean data set, and we even have a way to make sure that our future data will also be probably clean enough, we go to step 3, which is the step where we will actually build the model. So to build a model, we used a training set. The training set, we selected 70% of the whole data set. So you can see the training set on the right is in blue on the histogram. And also out of that, the whole data set, we took 30% of the data out to be used as a validation set. So again, the distinction is the training set, we will use that data set to build the model, and the validation set to then apply the model on those data and see what is the impact on the error we see, on the goodness of the fit, as you will see on the table in the bottom right corner. So we build a model, and to evaluate the adequacy, the accuracy of the model, we looked at the R-square. The R-square is actually, the maximum value is 100%. This would mean that the two predictors, A and B, are explaining 100% of the variation in tensile strength in the response. So the closer it gets to 100%, typically the better. And before you ask, no, I have no rule of thumb to say what is a good R-square. So it depends. And what we saw here is in the training set, we got an R-square of 96%, which was deemed good enough. But what is even more practical and more important is the error. And the error of the model was evaluated to be 1.04. I'm going to show you later what we do with that error and what that number means. And of course, we looked at the residuals from the model, which is again the difference between the value that the true value, the tensile strength that was measured, and the predicted value from the model. We looked at that. We saw that they were normally distributed. Variance was homogeneous, same variances for any of the tensile value we predicted, and also no trends over time independent. So we had we considered the model on the training set to be good enough. Then we tried the model on the validation set, and we saw that, as expected, the error increased a little. Why? Because now we're using the model on data that we did not use to build the model. So it's normal that the error will increase a little. So it increased to 1.33, but still, again, we had no issue with the residuals. So the number we need to remember now is the error we saw on the validation set, which is probably closer to the true error here that we will see in the future, is 1.33. So when I say we build a model, here to make it simple, I'm using a very simple model. It's what we call a multiple linear regression model. So the equation was the value of tensile is obtained by taking 50 plus 0.3 times the value you get from the sensor A minus 2.1 the value you get from sensor B. So for example, on that product, factor A, the value was 10.2, factor B, the value was 2.22. And the observed tensile was 47.4. However, if we apply the formula and we use 10.2 for factor A and 2.22 for factor B, we see that the prediction is 48.5. The residual is the difference between the true, what we call the true value, the observed value, minus the predicted value. So the residual is minus 1.1 here. So you see for every product that we use to build the model here, where we add a value for factor A and factor B, we can get a prediction, and we can also then calculate a residual. The lower the value of the residuals, the closer they are to zero, the better. So the lower the model error. So, but is the error acceptable? If you look at the right, I just showed here, it's again, conceptually. Conceptually, if I have specs from minus 10 to 10, and I measure a value here around 0, and the blue line, again, around that line there represents the prediction error. So my soft sensor is measuring a value there, but I know the prediction error is represented by the blue line. Then when I measure there, I know that it's great. I can get a value for potentially a product that I would never have measured. And if I use that value to compare to spec, the risk is 0 that I will really make a bad decision. Why? Because even because of the measurement, the prediction error, because of where I measured the prediction there, there's no risk that this product is within spec. However, if I get a predicted value here, with the error, I know that actually the true observed value could be outside of spec, even if my sensor is telling me that this product is within spec. So this is when I can be I'm more nervous about the decision I make, because there I could wrongly conclude that this product is actually within spec when in fact it's outside of the spec. So you see that the tighter, the lower the prediction error, of course, the more variability within the spec I can also accept. If you want to reduce the risk, because at some point you could observe, you could have a prediction that will be close to spec. And if you want to reduce the risk that you would potentially conclude it's within spec when in fact it's outside, one way to reduce that risk, but there's more than one, but an easy one would be to use tightened specs. So here what we did, we took the specs that were from 15 to 85 and we tightened them. So you see the dotted lines represents the tightened spec. And we tightened them using a formula. And my goal is not to show you the stats behind, but we tightened them by a value of 1.8 on each side. And because of that, there is now at least 95% chance that if we observe a value, a predicted value within the tightened spec, it will be within spec. Of course, when it's in the middle, it's, but overall, we reduce the risk because we have tightened spec now that we would wrongly conclude it. Because actually, if we now measure very close to the spec, because of the tightened spec, we'll conclude it's outside of the tightened spec. So it's potentially bad. So we won't consider it good. So that's how the risk is really reduced to eventually wrongly conclude that the product is good when in fact it is bad. So now that we have a model, we can do the predictions. For safety for our clients, we even tighten the specs a little when we compare, and we use those tightened specs when we compare the predicted value to the specs. We're now ready to monitor the process. Since factor A and factor B, remember those two, we measure every product. So now we can get a prediction for every product we make. The graph you see in the upper right corner represents for the products we measured the value that were obtained from factor A and factor B. And what we expect is that in the future, for when we are going to do the monitoring also, we expect factor A to be within that range and factor B within that range, because this is the range of values that we use to build the model. So of course, it's not bad to have some type of signal if at some point you measure a value of factor B, which is at 20, because then you would really be outside of the range that you use to build the model. So there should be an alarm. Perhaps the model is not doing a good prediction anymore. We don't know actually, because we are extrapolating. So on the graph here, what you can see is each blue point, each blue dot is a lab test. So before we started to implement the soft sensor, those were the results we had every hour and 10 minutes or so. The red dots, they represent the prediction that we have from the model. So of course, when in the past, we didn't have such a prediction, but we use those data to build the prediction. And it can show you how good the model is at predicting the variation in the blue dots. When we've implemented the soft sensor, then you can see that at the end, we have many, many red dots, because now when we did put the soft sensor on, we could predict every product. And what you can see is here a straight line to a next point. Why? Because this is at some frequency. And here it's not it could be once a day. We will do a hard lab test. We will do a tensile strength test and compare the result of that test to the soft sensor, just to make sure that the error we see is still in the expected normal range. But as you can see now, we can get a lot more information on the product we make because we measure all of them. And we can even potentially use this data to improve our capability to adjust the process, to adjust it faster. So again, here, that's the monitoring part. At a certain frequency, as I said, perhaps once a day, we will monitor if the model is still okay by comparing its predicted value to a lab test, a real tensile strength test. So an easy rule you can set is if you take plus or minus 3 times the error that you saw in the model, and here the error, remember on the validation set, it was 1.33. That was the model error here. So if you take plus or minus 3 times that, approximately, it should contain most of your error. So if you get outside of this range, it would mean that the error is really larger than what it should normally be. So you can potentially ask why. So for those of you who are familiar with control charts, it would be kind of using 3 sigma limits. So as an example, in this situation, I have let's say I do one check. So I have, for that product, I have the value measured by factor A, 46.1. Value measured by factor B, 4.49. From those 2 values, I get the prediction from my model, 54.7. To that, I add plus or minus 4, which is the potential error there. I compare that interval with a real tensile test I made on that product. The value I get is 53. So because 53 is within the prediction interval here, because it goes from 50.7 to 58.7, so 53 is within, I would say this is a green light. So at this point, I don't have any indication that there is a major issue with the model or with the lab test. Let's say I do another check. Factor A, factor B, I have those 2 on my product, build the prediction, and then I do my tensile strength test, and the value is 45.2. And this value is not within the interval. Then I would have a red light, because now the error is larger than what it should really be. And then this means I should look for a potential assignable cause for that. So is there something potentially wrong with the model or something wrong with the lab test? But something has changed. If you want to push it even further, rather than just using a check, because this type of check, green light, red light, it's easy to implement, but that's really some very basic check, a very basic check. What's even better would be to plot the residuals. Again, a residual, it's the difference between the predicted value, here it's 54.7, and the measured value. Sorry, it's the opposite. The difference between the real value and the predicted value. So here the residual would be minus 1.7. And we do plot those residuals on a control chart where the limits are set at 3 sigma. So here they are at plus or minus 4. What the control chart allows us to do, of course, like we did with the table before, the red light and all that, we can identify when a predicted value is too far from the observed value, and this should trigger a reaction. But also, we could identify trends that is also signaling an issue, even before you get a point outside of those limits. And often those trends are really, really interesting stuff, because what I've seen in practice, when we see them, it's often related to an issue with the soft sensor more than the hard measurement, because often those are already quite reliable. And the issue is that we actually have another factor out there, which is really affecting tensile strength, but it is not included in our model. So it's not factor A or factor B, it's a factor C. And so the fact that we have this trend is we should find out what that factor C is, what changed. And if we find it and we include that new factor in the model, including that new factor in the model will allow to bring the residuals back to 0. And we also just learned something. We learned now that factor C does have an impact on tensile strength. And we did not know that from the start because we never identified factor C as a potential predictor. So that's the very interesting learning part that you can get from your soft sensor. And that's actually also one of the big benefits the clients get when they do that is continuous learning from just improving the model over time.
So Martin, a quick question on the graphic, please.
Yeah.
Just looking at the fact, this is a normal distribution, best I can tell. In terms of as you were running this is quite interesting, the green versus the amber and stuff. But when this difference on that first data point out to the right before all the data points all exploded up there on the upper left, on that,
Yep.
I don't see any prediction within the data set that could have told me that I was getting to that point. So is this where that factor C might have come in? If I'd have been including factor C, I could have seen that guy coming?
Potentially, actually, actually it could be factor C created this outlier, and then another factor D created this trend.
Okay.
Or it could be factor C that created this, then this, because factor C suddenly somebody that was controlled in the past got out of control. So because in the past it was controlled, it never came out as a good predictor because something that doesn't change cannot explain variation in something else. But now it started changing a lot, and it does have an impact on tensile. So yes, it could be that factor C. For example, if it's a positive correlation, factor C had a big drop and it resulted in that first point. And then suddenly a big increase that stayed there for some time, which resulted in the trend we see at the end.
Good, thank you. Just one of the things that I'm sorry about taking up everybody's time, but if you look at the rate of change as these move back and forth across the green line, of these differences between the real versus the predictive, the change from that one data point to the very next data point where they all flew high and they stayed very high, that is pretty significant. And is there anything to be extrapolated from that?
Yes, now you're talking about, you know, if you're familiar with individual and moving range control chart, if I understand your comment correctly, you're saying
Yes.
here the moving range, so it's the distance between those two consecutive points is very large. So there must be something. Am I correct?
Yes, you are spot on. Yes.
So yes, I did not show it, but also if you want to an add-on to that, you could actually add to that a moving range chart that would allow you to detect that this is also a big change. However, again, that going down there and then up there, yeah, it's not normal. And the fact also that it's such a big change, it's also not normal, and we need to find the cause. And again, the cause could be, we don't know here, but it could be just factor C that really went out of whack. Major changes in factor C that typically was controlled because something broke. Or it could be just, factor C impacted there, and then it's another factor that just jumped in that created that variation. But you're totally right. According to the moving ranges we were seeing previously, this one is totally abnormal.
Thank you for that.
So as a conclusion, I know many organizations today, it's not rare that we have access to a large amount of process data. So the hard part today is not to get the data, it's to do something with it. And however, all that data can be often used to build decent models that could help in predicting quality characteristic. But when you do that, it's very nice, but just make sure again that you evaluate the risk then of using the prediction if you use that prediction to compare the value to specs. Okay, that's the small warning. There are unfortunately no rule of thumb, but make sure that you assess the risk then of potentially accepting a bad product. And what I've seen is over and above the potential benefits of having better capability to control the process, potentially lower frequency of lab measurements, because then you do your lab measurements only to check the soft sensor at a lower frequency typically than you were doing them before the soft sensor. A very good side product is learning, really learning because you're using a model, learning about what is affecting the quality characteristic. And so it's actually a good driver for continuous improvement. So this ends my presentation. I'm ready to take on your questions.
You can unmute yourself, or you can put something in chat. So don't be shy, please.
Well, if you all don't mind, I'm going to go again. Martin, we are
Go
just
ahead.
now at my plant. We just now installed the backbone for a plant condition monitoring system, whereby we're going to be able to pull off the transmitters and everything else that have already in place. And the hope is that we're going to be able to use it from an equipment reliability standpoint.
Mm-hmm.
First data over a period of time, and then watch the trend lines on vibration analysis or bearing temperatures and all these different types of things, and let us know, give us a predictive sense of when a piece of equipment is taking itself to failure, to where we can find time. If we don't find the time to take it offline, it'll take itself offline. So as a predictive thing, to be able to say, okay, if we leave this bearing in place for X number of period of time, then it's going to lay down on us. So I was very interested in that side of it, the data harvesting. We're working on that. Now you're showing me how I can utilize the data. This has been a very good presentation. Thank you.
Thank you.
Any questions?
if not, I can comment on just your comment. I think it's Sherman. It's Huma. You were the one
That
asking.
is correct. Yes.
Okay. So what is you know what is interesting with your data is, yeah, with all those things you measure that should measure some type of degradation on your equipment, like increase in variation or whatever. You know, when you build a model, you need a response, and here the response is stop. You know, the equipment stops because it breaks. So, you know, the small distinction potentially with your data is, I guess, what you will want to identify is what you want to predict is not stoppage. It's probably a change in behavior. So, for example, if vibration is normally stable to a certain level, if it starts increasing, I think that's the type of trigger you'll want, right?
Yes, absolutely.
And potentially combine that with some knowledge, process knowledge, to say, depending sometimes on the level of variation found, then you can potentially predict, and also the steepness of the curve at which the variation is increasing, you can then potentially predict failure without even observing any from people knowledge and the slope of the degradation in vibration, right?
I understand. Yes, sir.
So, but it's a little bit more complex than just having a response. So it's very interesting. It's an interesting setup. Because I don't see you saying, oh, I need to build my prediction model. So to build a model, I need to see failures. So let's run those equipments to failure.
We're hoping that if we can get to some data, stable data sets in terms of where the equipment is supposed to run, and then basically we could model based on that. We could establish specification limits, because right now we don't have any.
Yeah.
I think we could backfeed this into a program similar to what you're providing for us today.
Yeah, totally. And I'll know you'll be able to do that.
Sherman, you might think also, not just for what your application, not spec limits, but actually control limits. How does your process normally operate?
That's fair. Yes, sir.
Other questions or comments? I've got online, nope, nothing coming in. With that, I think we will close our meeting. If there's no other comments or questions from Martin.
I guess they're all asleep. I guess I was probably too boring.
Nope, I think that you had them on the edge of their seats. And I appreciate you taking time to share with us, and some very interesting application, and using the models to help understand what you're really being able to translate the terms you can measure often to terms that are more expensive and harder to measure, and being able to translate those in. They can add a lot of value in your manufacturing processes as well as other processes. You can actually, there's ways you could use that in the service industry, David, if you got into that. So there's a lot of issues there that you can learn from. So thank you so much for sharing that. We will have this posted online in a few days, as well as hopefully the video. I will try to get the video out there. I'm afraid to separate these two videos, because unless I do it offline, and I don't know how to do that very well. So the videos may be together, but I'll try to get them out there. Very good. Any other comments or questions? I'm going to stop recording if I can find my button.